Hi everyone. Today we're going to study Introduction to Vectors. Physical quantities can be classified into scalars and vectors. By definition, scalars are physical quantities having only magnitude and are not related to any fixed direction. Examples are distance, volume, area, temperature, time, etc. Also, by definition, vectors are physical quantities having both magnitude and direction. Examples are displacement, velocity, force, acceleration, etc. A vector quantity can be represented geometrically by a directed line segment, as we can see here. The magnitude of the vector is the length of the line segment, and the direction of the vector is the direction of the line segment. The vector here is denoted as vector AB. We put the capital A and capital B together with an arrow on top, or vector small a. We have a lowercase letter here with an arrow on top. The tail of the arrow, that is the capital A, is called the initial point of the vector. And the tip of the arrow, that is the capital B, is called the terminal point of the vector. By definition, the distance between the initial point capital A and the terminal point capital B of the vector AB is called the magnitude of the vector AB and is denoted by this notation. The vector AB is inside the two vertical line segments, or the vector A is inside the two vertical line segments, or simply as AB. The magnitude of a vector is also called its modulus or length. Note that vectors are generally denoted by lowercase boldface type. Here are the examples. And the scalars are denoted by lowercase italic type. And here are the examples. By definition, two vectors are said to be equal if they have the same magnitude and same direction. To illustrate, we have here two vectors A and B. These two vectors are equal. They have the same magnitude and pointing to the same direction. Today, we're going to study algebra of vectors. Let's begin with addition of vectors. If two vectors A and B are represented in magnitude and direction by the two sides of a triangle taken in order, then their sum, vector A plus vector B, is represented in magnitude and direction by the third side of the triangle, taken in the reverse order. For example, this is vector A. The vector B will come like this. The initial point of B will start from the endpoint of vector A. Now, for the sum vector A plus vector B, it becomes like this. The initial set of the sum will start with vector A, and the terminal of the sum will end at the terminal point of vector B. Now, subtraction of vectors. To subtract a vector B from A, we should reverse the direction of vector B and add to vector A. That is, vector A minus vector B equals vector A plus the negative of vector B. Suppose this is vector A and vector B is here. For the negative of vector B, it becomes like this. Now, vector A minus vector B is here. The initial point of the difference starts with vector A, and the terminal point of the difference ends with the terminal point of vector B. Now, multiplication of a vector by a scalar. Let vector A be any vector and M be a scalar. Then, the product M times vector A is a vector whose magnitude is absolute value of M times the magnitude of vector A. And direction is the same as that of vector A if the M is greater than 0, or we say that M is positive. And opposite to that of vector A if M is less than 0, or M is negative. For example, this is vector A. The vector 2 times vector A is here. We can see that the vector 2 times A is twice the vector A, and they are going on the same direction. And here is another example, negative 1 times vector A, or simply we say negative vector A. We can see that it is coming on the opposite direction, but of the same magnitude of vector A. We come now to the computation part. Let vector u equals x sub 1, y sub 1, and vector v equals x sub 2, y sub 2, be vectors in xy plane, and k be a scalar or a real number. Then, vector u plus vector v equals, this is the formula, an ordered pair where the x coordinate will be x sub 1 plus x sub 2, comma, the y coordinates, that will be y sub 1 plus y sub 2, and k times vector u. This is equal to k x sub 1, comma, k y sub 1. These are the formulas. Let us see this example. Let vector u equals negative 3, 4, and vector v equals 7, 6. We have here 4 problems. Let's begin with number 1. Vector u plus vector v. Our formula is here. Substituting the values, we have this negative 3 plus 7, comma, 4 plus 6. Simplifying now, we have this 4, 10. Second problem, vector u minus vector v. We have this negative 3 minus 7, comma, 4 minus 6. Then when we simplify, we have this negative 10, comma, negative 2. Third problem, vector v minus vector u. We have this 7 minus negative 3. So we write here 7 plus 3. Then 6 minus 4. Simplifying now, we have this 10, 2. Fourth problem is multiplication of scalar with a vector. 3 times vector u. Our formula is here. So we have this 3 multiplied by the vector u, negative 3, 4. So our answer is negative 9, 12. These are the answers. Today, we're going to study vectors in the plane. Consider a point P with coordinates xy in plane with respect to the origin O with coordinates 0, 0. The origin is here and the point P is here. Then the vector OP or vector V having origin and point P as its initial and terminal points respectively is called the position vector of the point P with respect to origin O. A vector in the xy plane is an ordered pair xy of real numbers. The numbers x and y are called the components of vector v. Also, vector v can be represented as a column matrix. That is, vector v equals the matrix xy. Let us discuss the magnitude or length of vector. The magnitude or length of vector v is given by this symbol. The vector v is enclosed in two vertical line segments. And this is equal to the square root of x squared plus y squared. This is our formula. For example, find the magnitude of the vector v equals 6, negative 1. Our formula is here. Let us substitute the corresponding values. So we have the square root of the quantity 6 squared plus the square of negative 1. Simplifying this, we have this 6 squared to be 36 plus the square of negative 1 is positive 1. So the final answer is square root of 37. Let us discuss vector joined by 2 points. Given the points A with coordinates x sub 1, y sub 1, and point B with coordinates x sub 2, y sub 2. The vector joining 2 points is given by capital AB with an arrow on top of it. This is our notation. The formula is the ordered pair where the x coordinate will be x sub 2 minus x sub 1. The y coordinates y sub 2 minus y sub 1. This is our working formula. This formula is also called component form of a vector. Example, find the component form of the vector with initial point A 2, 7 and terminal point B 5, 9. For our solution, this is our formula. Let us substitute the corresponding values. it becomes like this. This is now 5 minus 2, comma, then 9 minus 7. When we simplify this, we have 3, comma, 2. This is our final answer. Now let us discuss magnitude of vector joined by 2 points. Given the points A, x sub 1, y sub 1, and point B, x sub 2, y sub 2. The magnitude or length is given by this notation. The vector AB is enclosed in 2 vertical line segments. The formula is this big square root. X sub 2 minus x sub 1, this quantity is squared, plus the quantity y sub 2 minus y sub 1, this is also squared. This is our working formula. Example, find the length of the vector with initial point A 27 and terminal point B 59. Solution, we have this formula. Let us substitute the corresponding values. So we have this big square root, the quantity 5 minus 2, and this is squared, plus the 9 minus 7. This is also squared. Simplifying further, we have this 3 square plus 2 square. And it becomes the square root of the quantity 9 plus 4, and the final answer is square root of 13. There are some notes to remember here. Number 1, the vector 0 is equal to coordinates are 0, 0. Is called the 0 vector in the xy plane. The 0 vector is the only vector in the xy plane with length 0. The 0 vector is the only vector in the xy plane with no specific direction. The vectors I with coordinates 1, 0 and vector j equals 0, 1 are called the standard unit vectors of the xy plane. Today, we're going to study vectors in the space. Let point P with coordinates x, y, z be a point in space with respect to the origin O with coordinates 0, 0, 0. Then the vector OP or vector V having O and P as its initial and terminal points respectively is called the position vector of the point P with respect to O. A vector in the space is an ordered triple x, y, z of real numbers. The numbers x, y, and z are called the components of vector V. Also, vector V can be represented as a column matrix. That is, vector V equals this column matrix x, y, z. Let us study magnitude of vectors in the space. The magnitude or length of vector V in the space is given by, we use this notation. The vector V is enclosed in 2 vertical line segments, and this is equal to the square root of the quantity x squared plus y squared plus z squared. Example, find the length of the vector v equals 2, -1, 3. Let us write our formula here, then let us substitute the corresponding values. This is equal to the big square root 2 square plus the square of -1 plus 3 square. Simplifying now, we have this square root of the quantity 4 plus +1 plus 9. And the final answer will be square root of 14. Now let's go to vectors in the space joined by 2 points. Given the points A with coordinates x sub 1, y sub 1, z sub 1, and B with coordinates x sub 2, y sub 2, z sub 2. The vector joining 2 points is given by, this is our notation, AB, and there's an arrow on top. This is equal to the triple coordinates, where the x coordinate is x sub 2 minus x sub 1, comma, the y coordinates will be y sub 2 minus y sub 1, comma, the z coordinate z sub 2 minus z sub 1. This formula is also called the component form of the vector AB. Example, find the component form of the vector with initial point A, 7, 4, 5, and terminal point B, 4, 8, 3. This is our formula. Then let us substitute the corresponding values. So we have this 4 minus 7, comma, then 8 minus 4, comma, 3 minus 5. When we simplify, we have now this -3, 4, -2. This is the final answer. Now let us go to magnitude of vectors in the space joined by 2 points. Given the points A, x sub 1, y sub 1, z sub 1, and point B, x sub 2, y sub 2, z sub 2. The magnitude or length is given by this notation. The vector AB is enclosed in 2 vertical line segments. And the formula is this big square root, the square of the quantity x sub 2 minus x sub 1, plus the square of the quantity y sub 2 minus y sub 1, plus the square of the quantity z sub 2 minus z sub 1. Example, find the length of the vector with initial point A, 7, 4, 5, and terminal point B, 4, 8, 3. Our formula is written here, then let us substitute the corresponding values. So we have now this big square root, we have the quantity 4 minus 7, and this is squared, plus the 8 minus 4 is now squared, plus this 3 minus 5 is also squared. Then let us simplify further. 4 minus 7 is -3, then this is squared, plus 8 minus 4 is 4, we put the square, plus 3 minus 5 is -2, and this is squared. So we have now this +9 plus 16 plus +4. And the final answer will be square root of 29. Today we're going to study algebra of vectors in the space. Let vector u equals the triple coordinates x sub 1, y sub 1, z sub 1, and vector v with its triple coordinates x sub 2, y sub 2, z sub 2 be vectors in space, and k be a scalar, and this is a real number. Then vector u plus vector v. We can see that this is about addition of vectors. And the formula is here. It is also a triple coordinates. The x coordinate will be x sub 1 plus x sub 2, comma, the y coordinate is y sub 1 plus y sub 2, comma, the z coordinate z sub 1 plus z sub 2. And k times vector u. And this is about multiplication of scalar k with a vector. This is equal to this formula. We can see that the scalar k is multiplied to the components of the vector u. So we have k times x sub 1, comma, k times y sub 1, comma, k times z sub 1. These are the formulas. Example, let vector u equals 2, negative 1, 3. And vector v equals 3, 5, 1. Let us find or evaluate these three problems here. Let's begin with the first one, vector u plus vector v. We have our formula on this side. Then let us evaluate the sum. So we have here 2 plus 3, comma, negative 1 plus 5, comma, 3 plus 1. Then we simplify this into 5. This is 4 and this is 4. This is now the sum. Second problem, vector u minus vector v. So we have this 2 minus 3, comma, negative 1 minus 5, comma, 3 minus 1. And we simplify this into negative 1, negative 6, positive 2. This is now the difference. The third one is 2 times vector u plus 3 times vector v. Our formula for multiplication of scalar with a vector is here. So what we're going to do, we multiply 2 by the vector u added to 3 multiplied by vector v. So we have this 2 times 2, 4, 2 times negative 1 is negative 2, 2 times 3 is 6, plus 3 times 3, 9, 3 times 5, 15, 3 times 1, 3. Then we simplify the sum. This 4 plus 9 is 13, negative 2 plus 15 is 13, 6 plus 3 is 9. This is the final answer. Today, we're going to study properties of vector operations. Let vector u, vector v, and vector w are vectors, and c, comma, k are scalars. Then, property letter A. Vector u plus vector v equals vector v plus vector u. We can see here that addition of vectors are commutative. Property letter B, the group vector u plus vector v then plus vector W equals vector U plus the quantity vector V plus vector W. In here, addition of vectors are associative. Property C. Vector U plus vector 0 equals vector U. Property D. Vector U plus the negative of vector U equals vector 0. Property E. 0 multiplied by vector U equals vector 0. Also, 1 multiplied by vector U equals vector U. Property F. The scalar C multiplied by the product of scalar K by vector U is equal to the product C times K to be multiplied by vector U. Property G. Scalar C multiplied by vector U plus vector V is equal to C times vector U plus C times vector V. Also, the quantity C plus K is multiplied by vector U. This is equal to C times vector U plus K times vector U. These are the properties of vector operations. Today, we're going to study linear combination of vectors. A vector V is said to be a linear combination of the vectors u sub 1, u sub 2, u sub 3, up to u sub n. If there exist scalars k sub 1, k sub 2, k sub 3, up to k sub n, such that vector V is equal to k sub 1 times vector u sub 1 plus k sub 2 times vector u sub 2 plus k sub 3 times vector u sub 3 plus up to plus k sub n times vector u sub n. In xy plane, any vector in this form, vector u is equal to the ordered pair x sub 1, y sub 1, can be written as a linear combination of the two standard unit vectors I is equal to 1, 0 and j equals 0, 1. As follows, vector u is equal to x sub 1, y sub 1. And we will show this to be equal to x sub 1 times the ordered pair 1, 0 plus y sub 1 times the ordered pair 0, 1. So in here, we're going to substitute the value I to this 1, 0. Also, we will substitute the value j for this ordered pair 0, 1. So we will have x sub 1 times I plus y sub 1 times j. This is the linear combination. In the space, any vector in vector u is equal to the triple coordinates x sub 1, y sub 1, z sub 1 can be written as a linear combination of the three standard unit vectors I equals 1, 0, 0, j equals 0, 1, 0, and k equals 0, 0, 1. As follows, vector u is equal to x sub 1, y sub 1, z sub 1. And this is equal to x sub 1 times the three-pole coordinates 1, 0, 0 plus y sub 1 times the three-pole coordinates 0, 1, 0 plus z sub 1 times the three-pole coordinates 0, 0, 1. In here, we're going to substitute the value I for the three-pole coordinates 1, 0, 0. We will substitute the value j for the three-pole coordinates 0, 1, 0. And we will substitute the value k for the three-pole coordinates 0, 0, 1. So we have here x sub 1 times I plus y sub 1 times j plus z sub 1 times k. This is our linear combination. Example 1. Write each of the following vectors as a linear combination. Let's begin with problem I. Vector v is equal to 3, negative 5. We can show that this is 3 times 1, 0 minus 5 times 0, 1. And this will now be equal to 3i minus 5j. This is the answer. Problem double I, vector A is equal to 7, negative 2, negative 6. We can show that this is equal to 7 times the three-pole coordinates 1, 0, 0 minus 2 times the three-pole coordinates 0, 1, 0 minus 6 times three-pole coordinates 0, 0, 1. We will now replace the three-pole coordinates with I, j, and k respectively. So, our final answer, 7i minus 2j minus 6k. This is the final answer. Example 2. Let vector u equals 2, 3, 1. Vector v equals 0, 0, 2. And vector w equals 4, 0, 1. Find the linear combination vector u plus 2 times vector v plus 3 times vector w. So this is what we're going to evaluate. We're going to substitute the corresponding triple coordinates. It becomes like this. The vector u is here plus the scalar 2 times the vector v plus scalar 3 times the vector w. Simplifying further, we copy the vector v down here plus we evaluate the scalar 2 by the triple coordinates. So we have here 0, 0, 4 plus the scalar 3 multiplied by the vector w 4, 0, 1. So it becomes 12, 0, 3. So the final answer will be like this. 2 plus 0 plus 12 is 14. 3 plus 0 plus 0 is 3. 1 plus 4 plus 3 is 8. This is now the new vector. Translating this into linear combination, we have now 14i plus 3j plus 8k. Today, we're going to study collinear vectors. When two or more given vectors lie along the same given line, then they can be considered as collinear vectors. For illustration, we have here three vectors. They lie along the same given line. They are collinear vectors. We can consider two parallel vectors as collinear vectors, since these two vectors are pointing in exactly the same direction or opposite direction. Here we have two parallel vectors. They are collinear vectors in same direction. Another example, we have two parallel vectors and they are collinear vectors in opposite direction. So this is now an example of two non-collinear vectors. If vector u and vector v are collinear vectors, then we can find a scalar k such that vector u equals k times vector v. Two vectors u and v are considered to be collinear vectors if and only if the ratio of their corresponding coordinates are equal. This condition is not valid if one of the components of the given vector is equal to 0. Example, check whether the vectors 3, 4, 5 and 6, 8, 10 are collinear or not. We say that two vectors are considered to be collinear vectors if and only if the ratio of their corresponding coordinates are equal. So what we're going to do here, we're going to put a ratio of the coordinates respectively. We start with 3 and 6. So we write here 3 over 6, followed by the 4 and 8. So we have 4 over 8. We can see that 3 over 6 is equal to 4 over 8. Then we have 5 and 10. And we write here 5 over 10. Here, the ratios of the corresponding coordinates are equal. We can simplify each of these into 1 over 2, or 1/2. Therefore, the two vectors are collinear. I hope you learned something from this video. See you again next time.